My presentation is about understanding the rats and a history of a failure. I think the best way to learn is learn from the mistakes, and probably the best way is to learn from others' mistakes, not our own. That's why I want to talk with you about one of my projects. Actually, it was my master degree project, and I hope that you learn something from my mistakes. So first of all, why do we want to understand the rats, and how it came that I worked on it? During my studies, I was looking for a topic for my master degree for the thesis, and the scientists from the PAN came to us asking if we can help them with one problem, because they are testing some drugs for depression on rats, and they need to know what are the rats' emotions. When you look at the rat, you can't really tell if it's sad, if it's hungry, if it's happy or scared. So what is a way to know if the rat is happy or sad or something is we can just listen to them. But the rat sounds are in this frequency, but the human ear can't hear it. So we need to use some specialistic microphones. We need to record them and then manually find out what are the emotions. And previously, the scientists were using it like manually looking at the recordings and manually tagging them with the emotions of the rats. But on the long term, it takes a lot of time to tag the recordings. So I thought it would be nice to someone to use some machine learning or something, and to make computer understand the rats. So basically understand the rats language. So if we look at the spectrograms of the recordings, you can see there are different types of calls. When we are looking at the recordings, we can clearly see what are the types, right? So we can see that there are some more complex, some smaller ones, some are just like one line, some are like a few small signs. So we came to the idea, okay, so we have this very long, 6-minute long recording of an experiment, and how we can make it, how to tag it. So first of all, we need to, I think I skipped, we need to read the file. And basically, that's the first thing, but seems like quite easy task, right? So what I did, okay, so they were using some specialistic tool for seeing the spectrograms that is normally used to detect the sounds of elephants, if I remember correctly. So I tried to reproduce it with Python. And the image on the left is the image I got. And it was like, it doesn't looks at all like their spectrograms. And really, it's one of the simple problems, but when I tell you the solution, it just sounds, oh, easy, come on. But I spent really too much time on it. The reason this spectrogram was looking so bad was because of the sampling rate I was using when reading the data. It's one of the parameters that in both Python libraries and in the program used by the scientists was set as some default, and no one was thinking about it. So if you don't think about some parameters, you don't even think that you should change it. It took us like a month, I think, to find out that I was sampling rating with 22,000 frames per second, and I should have with 200. So a small change in the code, changing only this parameter, and I just get these spectrograms. So we have the spectrogram, and now we want to train our model. So first, I have already this spectrograms, I need to think about two things. First, the strategy I want to use to learn my computer to understand the rats. And second, how should I put the data into machine learning neural networks, So first thing, the strategy. We thought what the best strategy is if I have this spectrogram right here, we should use first some neural network to divide it to see, okay, here is a sound, here is a sound, here is another sound. So to divide the spectrogram and extract the places where we see the sound, and then use another neural network to classify if this sound is the same type as this or maybe something different. So first thing first, we need to detect the sounds in the spectrogram. We want to use VGG and other image-based neural networks, and spectrogram is in fact two-dimensional dataset. So we need to make it three-dimensional, so it will go into neural network in some easy way. So here is the diagram that shows what we did. So we basically took each three rows and combined them into one row that was like a row of the image. So if we look at it as a image, we would see that from the spectrogram, the first row is R, the second is G, the third is B, and again R, G, B, R, G, B. So we kind of squished this image, and we just, because after performing the Fourier transformation, we had 256 rows, and it's not dividable by 3. We just decided to delete the last row because we can see from the spectrograms, but at the very lowest place we can't see any sounds. They are much higher, so this row shouldn't make any difference. So after making the images, so this is like squishing, but then wait, we have like 6-minute long recording. And we want to somehow put this recording into the neural network. So we can't just have like 6-minute long, 200,000 frames per second. It makes a huge file, and it would be useless. And so we divided this file into small pieces. So looking at the spectrogram, we took every 85th columns of the spectrogram, and we decided to put it into two groups. Into the group with noises, so there is no rat sounds, no squeaks, and into the group of squeaks. Into the noises, we put every image that had not any column was tagged manually, and in the squeak, we put the images that the middle column was tagged somehow by the scientist. So then we used a few models. We used something called transform learning. So we used ResNet, VGG, and ImageNet pre-learned neural networks. And we tried to retrain them to transfer the learning for this. And also we used a small experimental neural network, which we learned from the beginning, and trying our best to find an architecture that will give us good results. So let's see how the networks were learning. On the left, we have the learning from the training set. And if we look at it, it looks basically okay. Two of the networks are getting almost 100% right. But if we look at the right, and it's the learning curve based on the set that was used to check the training during the training, right? it doesn't look at all like it's learning. It's like one of them, the experimental one, has a nice curve for it, but the others are like, what's going on? So after much of training and trying our best, we decided to look into the results. So we we checked on the blue ones is the recording we use for training. The red ones are the recording used for after the training to check how our neural networks were behaving. And we count how many images from the spectrograms are tagged or not tagged in both our network and in the tagging by the scientist is manually one. So if you look at it, it looks mainly okay. It's even kind of nice, but in case of every network, we had better results with the set that wasn't used for training, and basically all have above 80% of the accuracy. Only the learning of ResNet has lowers. But when we looked at the results, it wasn't looking like it's true. So I decided to basically the same statistic, but I excluded from the counting the images that were both untagged by my network and by scientists from the counting. So here are only counted images that were tagged somehow or my network or scientists told that, hey, here is some sound. And now we see that the results are terrible compared. We have like 40% or ResNet has like 0. And so here it looks basically like a little bit around flipping the coin. So how the results are looking. Here on the two spectrograms, these are results from two of the networks we use. The small bluish box are the tag from the scientist. These high ones, dark blue and pink here, are by my network. And here we have a fragment with lots of sounds, so probably two rats were talking to each other or something. And we see that basically all the boxes are somehow off or even outside of the sound entirely. So I looked through the whole 6 minutes long recording, and here if you looked, it's like 2 seconds of it. And it appears that probably the reason for it is that these sounds have lots of noise, but when I was training the models, I make sure that the data for tagged and untagged images are the same. So it shouldn't be that, well, you have like lots of noises in one data set in the recording. If I wasn't training on a whole recording, but only on a small size of it, because I wanted my data to be balanced. So I had the same amount of samples with sound and the same amount of samples with noise. So then, when I was first talking about it after I finished working on it, and I said, okay, I won't touch it anymore again because I will go mad soon. Someone asked me, hey, could you play me the sound? And when it kicked me, okay, I didn't prepare my data, or I didn't prepare my data correctly, because when I played the sound, it was just noise all over. So let's go to what went wrong. First of all, the origin of the idea. Because I was looking for any topic for my master degree, I was firstly looking at some image transformation using machine learning, and then I came into the sound stuff. But before I did some research on image, So I use the same methods as for image processing in neural networks. And in fact, sound is not an image. And this is the thing I think I should consider earlier. Yes, you can use some of the neural networks trained on images for doing something with sound, but it won't have as good results as using some maybe smaller, maybe different neural networks. Here I use only convolutional ones, which are really complicated neural networks. So probably some easier algorithms, easier neural networks would work better because sound is in fact one-dimensional data, not three like images. So I think it was wrong. The third, which I started talking already, is prepare your data properly. And yes, I didn't dissolve the noise because I was looking at the spectrograms, and I was so much focused on this image part of it. So looking at the spectrograms, not even trying to hear the sounds and think how the terraces are, how it works. And in fact, afterwards, I tried some redoing my work by clearing my data. And then when I played with rats again, I could hear the squeaks they made. So I was like, oh my God, that's why it felt so miserable. So remember to prepare your data and try to look at it from every point possible before you decide what's it. And in fact, afterwards, I tried a small experiment. I didn't get deeply into it, but I think if I go further, it would be working better. For detecting the sounds in a recording, probably some easy algorithms, like if there is in some window the numbers, because sound is saved as a numbers in the file, right? So if the numbers are in some range, then this is a sound, and if not, this is a noise. And when I tried something silly like doing this window through the recording, I found out that it was better for my neural networks on which I was working for like a year. So a little bit of disappointment that I spent so much time on something that could be really easier done. But I was pushed towards using neural networks and couldn't use any other things. And the last thing, don't wait. Don't go into this, I need to use neural networks. I can't use simpler algorithms. And ask quasars. If you are talking only with one person, you are probably both going into the same direction and you are standing in the same corner, thinking why you are facing the wall and can't go further. Ask someone else. Conferences are a great place to ask questions. Probably some of you who works with neural networks more are already thinking, oh my God, she should have done this or that. So I think this is the best place to ask questions, ask different people. Don't hesitate to talk about your struggle and just don't keep to yourself your problems. Talk about it. And I hope that you all think you will all remember from this presentation that asking people and talking about your problems is the best way to find solution. Because afterwards, I finished this thesis with, okay, I failed because of that and that, and I'm a master, so I have this master degree. But I think if I was asking other people during my thesis, the end result wouldn't be like, okay, I failed with it miserable, but probably I would be able to understand the rats right now. So here you have you can find me on Twitter, LinkedIn, and Discord. I will be probably available on Discord more than only today. And now we have time for some questions, if anyone has any.
Thank you very much for this topic.